In this second video from Chapter 8, we're now going to discuss the distribution of the sample proportion. In the first video we discussed mean, now we'll discuss proportion. Remember, proportion is simply just a fraction. In this case, the proportion of, let's say, people with blue eyes is 20%. So 0.2 would be the proportion. P is going to be the population proportion. P hat is going to be the sample proportion. Okay, so those are going to be the two variables we will use for population and sample. So let's suppose that a random sample of size n is obtained from a population in which each individual either does or does not have a certain characteristic. The sample proportion, denoted as P hat, is going to be given by the number of people or individuals that have that specific characteristic, in case maybe blue eyes, divided by how many people were in the sample. In other words, that proportion is going to be a statistic that will estimate the population proportion P. For a simple random sample of size n with a population proportion of P, the sample of the sampling distribution P hat is approximately normal, provided that this is true. In other words, n and P, which is the population proportion, have to be large enough so that way when we multiply it by 1 minus P, you get a number that's greater than or equal to 10. So both n and P have to be large, or one has to be large if the other is going to be small. The mean of the sampling distribution is given by the average of your sample proportions, and the standard deviation is going to be given by this value over here. So we're still discussing shape, center, and spread, but how we find shape and how we find spread are different than how we found them with the means. So make sure you're using these three characteristics for proportions, not the characteristics we discussed for mean in the previous section. So if I were to ask you a question, let me leave those formulas there. According to a study that was done by Pew Research Center, 39% of adult Americans believe that marriage is now obsolete. So suppose a random sample of 500 adult Americans is asked whether marriage is obsolete. Let's first describe the sampling distribution of the proportion of adult Americans who believe marriage is obsolete. So remember, when you're asked to describe distributions, we're talking about shape, center, and spread. So you've got to discuss all three parts. When we're discussing shape, we're usually looking for it to be normal. So you have to prove that this distribution is normal. Since it did not state that the population was normal anywhere in this problem, I cannot assume that the sample distribution is normal, unless I can prove this. Can I prove n, which in this case is 500, times p, in this case is 39%, times 1 minus p, can I prove that that is greater than or equal to 10? If this is true, then we can say that the sample proportion is approximately normal. Which it is. The center is going to be located at the average of all of your p hats. In this case, it's going to get closer and closer and closer to the population parameter, which is 0.39. So there's no math that is involved in doing that particular example. The spread is the distribution and how widespread your data is. So the spread for this one is going to be my standard deviation. The standard deviation of my p hats is going to be the square root of the population proportion, which is 0.39, times 1 minus the population proportion, divided by n, in this case is 500. Now all of that is under the square root. And when I put this into my calculator, I get 0.0218. So I have discussed the shape, it's normal, which means it's symmetric. Here's the middle, and here's how widespread the data is. So what then is the probability that in a random sample of 500 American adults, less than 38% believe marriage is obsolete? Well, we could draw a normal curve. Since we've proven that it's normal, we can draw a normal curve for this to kind of get a better picture of what's going on. We know that this is symmetric or normal, and we know that the center is going to be at 0.39. This particular question says I'm going to go into my hat of names, and I'm randomly going to pull out one out of the 500, and I want to know what the probability that in this random sample of 500 names, I'm going to select less than 38% that believe marriage is obsolete. So obviously 38% is going to be on the left-hand side, and I want the probability of it being less than that. So I'm looking for this blue probability on the left-hand side. So to find that, I do exactly the same methods that I used from chapter 7. I'm looking for the probability that the sample proportion is going to be less than 38%. So first thing I do is I find that z-score. So I'm looking for the probability that that z-score is going to be less than what number. So I have to turn 0.38 into a z-score. To do that, I take the data minus the mean, which is up here, 0.39. We divide that by the standard deviation, which we found right here, is 0.0218. So I find a z-score that is negative 0.46. So all of these things say the same thing. The p-hat is 0.38, but I had to turn that into a z-score, and this z-score of this value is negative 0.46, and we know it's negative because it's on the left-hand side of the mean. Then I go to my normal distribution table, which for us is table 5, and then I look up a z-score of negative 0.46. So negative 0.46 is going to give me a probability of 0.3228. So this area right in here, probability is 0.3228. So for part C, what is the probability then in the same random sample of 500 adults that between 40% and 45% think that marriage is obsolete? So let's go ahead and draw another picture. This time I want to shade in the area that has between 40 to 45%. So here's 40, here's 45. And I want to know what this shaded area is of everything in between those two lines, right? So we're going to do the same thing we did up here. We're going to find the z-scores of each of these data points. Then once you find the z-scores of each of those, we're going to subtract those probabilities. So here's, we're going to find the probability that p-hat is in between 0.40 and 0.45, which means I need to find the probability that z is in between what two numbers. So to find the z, I have to find each of them independently. The first z is going to be located at 0.40 minus the mean, which is 0.39, all divided by the standard deviation, which is 0.0218. Notice the standard deviation is not changing each time because we're not changing our sample size. Sample size is 500 for all of these examples, so we haven't had to change our standard deviation. Now if your sample size did change, you'd have to change your standard deviation down here, which we found up here. It used a sample size of 500 for this number. So this z is going to be 0.45 minus 0.39 over 0.0218. So those two z-scores are going to be 0.46 is going to be the lower, and 2.75 will be the upper. So I look up those two z-scores in my table, and I find two different probabilities. The probability of the bigger z-score is 0.9970. The probability of the smaller z-score is going to be 0.6772. And when I subtract those two probabilities, I get 31.98%. And that's going to be the probability of this blue shaded area right here. So for the last question, it says, would it be unusual for a random sample of 500 adult Americans to result in 210 or more who believe marriage is obsolete? So the first thing we got to do in these last examples, we already knew what the p-hat was that was given to us. It gave us 40% and 45%, which were the two p-hats. This question doesn't give us p-hat, so we have to be able to find it. In order to find p-hat, remember, it's the number of successful items divided by n. In this case, we're looking for 210 out of 500 that all feel the same way that marriage is obsolete. And when I divide those two numbers, that means 42%. So now that I have p-hat, now I can go and do the problem the same way I did the previous ones. If the mean is 0.39 and p-hat is 0.42, I'm looking for the probability that that many or more, so 42% or more, feel this way. So I'm going to then turn this probability into a z-score. Z-score is going to be 0.42 minus 0.39, all divided by 0.0218, which is going to give me a z-score of 1.38, which equals, if I go to my z table, table 5, I look up a z-score of 1.38. 1.38 is going to give me 0.9162. It's going to give me a probability of 0.9162. Now remember, that probability is the left of a line. I don't want the left-hand side, I want the blue shaded area. So to find the right side, I have to subtract 1 minus that probability, which gives me a probability of 0.0838. So this is the probability of that blue shaded area. I didn't finish the question though. The question said, would it be unusual? In other words, is this probability unusual? And the answer is no. It is not unusual because it is not less than 5%. So let's keep going with this same, nope, I got a new one. So my new activity is going to be this one right here, which typically I would do in class, but I'm going to do it in the video. Okay. According to Mars, which is the company that owns M&Ms and a lot of other delicious candies, the distribution of colors, this was last released in 2008, for bag of milk chocolate M&Ms contains 24 blue. Okay? Your bag of M&Ms, I'm going to hand you out a bag of M&Ms, and I'm going to do a bag of M&Ms here in the video. My bag of M&Ms should contain somewhere around 50. I've done this activities many times, and every plain size bag of M&Ms usually has around 50, usually around 53, 54 M&Ms. But don't eat them just yet. What we're going to just do right now is we're just going to pour 10 M&Ms out of the bag, right? So I have a bag in front of me, and I'm going to dump out 10 M&Ms, and I'm going to leave the rest in the bag. So I'm just going to pour out 10, and that's going to be my sample size. And I'm going to consider that random because it's just going to be the first 10 that come out, right? So I'm going to count how many are blue out of the 10 that are in front of me. So I poured 10 M&Ms out of the bag, and I found that I had 2 blues out of the 10. So far, the proportion of blue, if I were to stop right here, is going to be 20%. Clearly, we could make those percents, but for the sake of this table, it says express it as a decimal. All right, so now I'm going to go back to my bag. I'm going to pour out another 10. In other words, now I'm going to have 20 M&Ms sitting on my table in front of me. When I pour out another 10 M&Ms, I have not only the 2 blues from the first 10, but now I have an additional 4, which gives me 6 total blues that are sitting on the table in front of me. So the proportion of all blue M&Ms is going to be 6 out of 20. So now I have 30% blues. So you can see that these individual p hats, these are p hats. Each of these p hats are different from each other. But I'm increasing my sample size. By the time I get to the bottom, I'm increasing my sample all the way up to 50, which is almost the whole bag. This proportion should be getting closer and closer and closer to what the true proportion of blue M&Ms is. So let's go ahead and pour out an additional 10 M&Ms. So now I have 30 sitting in front of me. Well, I had an additional 2 M&Ms fall out, so that gives me a total of 8 blues in front of me. 8 out of 30 gives me a probability of 27% blue. Let's keep going. Pour out another 10. I only had 1 blue extra come out, so that gives me a probability of 23% blue total out of those 40 M&Ms. If I pour out an additional 10, I had 5 blues fall out of the bag, which means I have a total of 14 blues. Out of the 50 M&Ms that are sitting in front of me, that gives me 28% blue. Now, of course, there's a couple extra M&Ms left in the bag. I am just going to go ahead and eat those, okay? So now what you're going to do is you're also going to count the total number of M&Ms you have for each color and record those frequencies. We are not going to use them in this chapter, but we will use them later in the course. So whatever we record here is what we'll use later on. Okay, so let's go ahead and count the colors. In my particular bag, I had 9 red, 12 yellow, 15 blue, and you'll see that it doesn't match the 14 because I had 54 M&Ms total. Remember, I only went up to 50. I had 4 extra M&Ms. There must have been a blue in that extra. I had 6 green, 3 orange, and 9 brown. Now, of course, your distribution is going to look different. It would be very unusual if you picked out the exact same distribution that I had. So after you've done all this, you can eat your M&Ms while we think of the following questions, and let's start to solve some of these. It says, first we're asked to describe the sampling distribution. We obviously want to address 3 different topics: shape, center, and spread. The center is going to be the true proportion of blue candies in the population of all M&M candies, not just our sample. So let's assume we don't know what the true proportion is. In this case, we actually do. The true proportion was 24% because that's what, up at the top of the page, that's what Mars Company described it as, although that data is it's over 10 years old. It was back from 2008. So we don't truly know if this is what they're striving for anymore. So if you don't know, or maybe you're trying to go against this grain with a different thought process, what would be then your best guesstimate for the population parameter? What would you guess this is if you didn't know that this was true? Okay, I would probably guess which of these numbers up here. Would I guess the 20%, 30%, 27, 23, or 28% blue as my population parameter? I would probably pick the last one, only because it had the largest sample size, and we know as the sample size gets bigger and bigger, the numbers get closer and closer and closer to what the true population proportion is. So I'm going to use 28%. For me, for my bag, I'm going to use the mean of all of my p hats, which gets closer and closer to 28%. And I'm going to assume, we'll infer that that's close to the population parameter. Now yours, again, might be different. The spread is going to be the standard deviation. Okay? The standard deviation of p hat is going to be the square root of p, in this case is 0.24, times 1 minus p divided by n. In this case, we're going to use 10. it told us to use n as 10 for this first example. Clearly we have more than that, but we're going to use the sample size of 10 for this first example. Okay, so finally onto the last page. Now let's calculate the standard deviation of n as 50. So we're going to do the same thing. We have p times 1 minus p divided by 50, and we take the square root of all of that, and we get a standard deviation that is much smaller, 0.0604. So you can see what's happening to the standard deviation. As n gets bigger and bigger, that means we're dividing by a big number. That means your standard deviation is getting smaller. So as n is increasing, your standard deviation, in fact, should be getting smaller. Now finally we got to describe the shape. We did the center and the spread, now is the shape. Shape, we want to be able to determine that it is normal. And from the previous pages, in order to determine that something is normal, we have to prove that np 1 minus p is greater than or equal to 10. In order to prove that, we have to determine how many n's we need. How many M&Ms do we have to sample in order to assume that the sample is normal? So we could work this backwards. If we don't know what n is, let's just plug n as the variable n. We know that p, for this example, Mars Company said p should be 0.24. And then we solve this inequality for n. So what we have to do is we have to divide 10 by 0.24 and also divide by 1 minus 0.24, which is 0.76. And when we do that, we get n should be greater than or equal to 55. Okay, now unfortunately my bag only had 54 M&Ms. So in order to prove normality, I was supposed to have at least 55. So I am just a tad shy. So we'll assume I've met that prerequisite so that way I can continue with the rest of this question. But unfortunately, I really should have had a bag of M&Ms with at least 55. But we're pretty close. So we'll assume, again, I'm assuming that the sample was normal. So let's increase to a larger size bag. Let's say I took out 100 M&Ms from one of those great big M&M bags. And I want to find the probability that less than 20% are blue. Okay? So I'm looking for the probability that my p hat, out of these 100 M&Ms, that my p hat is less than 20%. So again, the first thing I do is I find the z-score. You guys know how to do this by now. We take the data minus the mean, which in this case the average proportion should be 0.24, divided by the standard deviation. Now it's going to change because my sample changed to 100. It's not going to be the same as it was up here because that sample was for only 50. So we have to change our standard deviation. Standard deviation is going to be 0.24 times 1 minus 0.24 over 100. So it might be best to calculate all of this in the denominator first and then do your division. Or if you're good with your calculator, you can do all of this at one time. But be very careful that you put in the right parentheses. So the probability of z is got to be less than or equal to negative 0.937. That's what I get when I put all of this in my calculator. And when I look up that z-score into table 5, I get a probability of 17.36%. What is the probability that more than 30% are blue? So the probability that p hat is more than 30%. So we're going to do the same thing. My z-score is going to be 0.30. It's the only thing that's going to change from the example above. My standard deviation is going to be the same because I'm still dealing with the same sample size of 100. So that means my z is going to be 1.41. And when I look up that probability, or excuse me, that z-score in my probability table, I get 0.0808. How about between? What is the probability I'll randomly, out of these 100 M&Ms, what's the probability I'll get somewhere between 26 and 28% that are blue? So we're looking for the probability that my p hat is somewhere between 0.26 and 0.28. So we have to find each individual z-score. The first z-score, I do the same thing that I did up here. Now that you know what to do, all we got to do is put in 0.26 here and then 0.28 for the next one. So I'm going to go ahead and give you the z-scores. Certainly you should calculate these on your own. Here's the two z-scores. So I looked those z-scores up. Most z-tables only have 2 digits that you can use. So I would use 0.47 for this one. I use 0.94 for this one. And I'm going to get a probability of 0.8264 for the first one and 0.6808 for the second one. And when I subtract those two numbers, I get 0.1456. So if I total up all of the blue M&Ms that you had all together in your bag and calculate the value of the sample proportion, n may be bigger than 50, determine whether your group's results were unusual, assuming 24% is the true proportion. Hint, calculate your z-score and find the proportion of observations that are unusual or more unusual than your own. From my particular example, my bag of M&Ms, my p hat was 15 out of 54 total, which gives me a 0.28 or 28% blue, right? So then I'm going to turn that into a z-score real quick. So my z-score is going to be 0.28, which I have done up here already too. 0.28 minus 0.24, but of course my standard deviation is different, so I will get a different number. 0.24 minus 1.24, and all of that's divided by n. In this case, I had 54 M&Ms in my personal bag, which gives me a z-score of 0.69. So what I'm going to do now, okay, so I found the z-score of 0.69. Before I go to the table, let's go ahead and take a peek at what this is going to look like, right? We know that the average amounts of blues should be 0.24. Now my particular sample had an average of 28% blue, which is going to be over here, right? Okay, and it wants to know if that would be unusual, right? Unusual usually states that you're on the outside of 2 standard deviations. Standard deviations, anything outside 2 deviations, anybody out here in this green area outside of 2 deviations from the mean is considered unusual. So my question is my bag that has 28% blue M&Ms, is that considered unusual? It's not considered unusual because the z-score is 0.69, which is inside a z-score of 2. Anything outside of 2 is unusual. Since my data is inside 2 deviations, it only has a z-score of 0.69, this would not be considered unusual. So my bag of M&Ms that has 28% blue is not an unusual thing. Even though I know that it should be closer to 24%, 28% would not be considered unusual. So I did not have an unusual bag. So my question is, did anybody in class have an unusual bag of M&Ms? Did anybody have a bag of M&Ms that was more than 28% that was out here in the green area, or had a z-score that was out at 2 point something or negative 2 point something, meaning you were out in the unusual area? So the last question then says, Mars claims that 24% of chocolate M&Ms are blue. Does the information that we found here seem to support this claim? Why or why not? So I'm actually going to leave that to you to kind of think about. We would normally discuss this in a class, but I'd like you to just think about that, and we'll talk more about company claims in chapters 9 and 10, which follows.